All right, perfect. Thank you so much, ladies and gentlemen, and welcome to our day 3 part of the training on understanding the different concepts of GIS and remote sensing, tailoring for Earth monitoring. As we mentioned before, if somebody wants me to allow them to record. Okay. All right. So as I mentioned, Dr. Weisler is going to come in at some point to just give us a quick recap of what we have done. So Doctor, I don't know if you are there and you are ready. Doctor?
Hello.
Hello.
Yes, I think I'll be able to just say before I give this recap, because I'm realizing that the time is running fast, and we have quite a lot, because the remote sensing part is not yet covered, but we are still on the GIS part. So I'm not going to really say much this morning. I'll try to see how I put all these together to make sure that we are able to cover it up. But I think what I can say now is that based on what I've been following, because the whole of yesterday I had other engagements, although I was following a bit. The reality is that we are moving fast with the covering the aspects of GIS, from where you started with the definitions, you are looking at components. Those are all aspects we are looking at. I'm hoping that we shall be able to have a look at the applications, some applications. But notice what I'm realizing is that we are giving you quite a lot in a short time, and in one or the other, it is by design, because this is a basic course which we expect you to be able to utilize in the subsequent courses that we shall be inviting you to apply for, such that you participate. So I'm just requesting that you put in a lot of time, put in effort to learn these basic things, because when we move into the other components, like the applications Mr. Eugene was talking about, then it will be quite difficult for you to understand or appreciate those ones when you don't know the basics. So I'm requesting that you put in time, and then make sure that, making sure that you pick all these concepts. We are here to support you. And then when we ask you to apply for the other courses, you are in a position to follow up very well. So I'll not give a full recap this morning, but all I want to say is that we are on course, although we have quite a lot to prepare, to give you. And with that, I'll request that Mr. Nuru continues with what he has for this morning. I'll be in following, and I'll be coming in here and there until that time when I also have to deliver something to you as we have agreed. So on that note, I just said that, Mr. Nuru, please, let's run a bit faster. I know some people complain, but we don't have a choice. Let's run faster. We are certain that with our continued support and the fact that we have put this course even online and we are available, then it will be easier for you to be able to pick up these concepts. So thank you very much.
Thank you very much, Doctor. Just like you've just mentioned, let's dive into the the part of the actual training as we move on. Thank you. All right, so next, so basically we are going to handle these concepts today. We're going to look at databases, spatial analysis and tools, and then dive into GIS applications. Hopefully when we have some little bit of time, then we can do a few hands-on using QGIS, just to understand how do you open QGIS, how do you add layers there, and how do you do ABCD from there. Just trying to understand the interface and try to understand the different data models. What are vectors, what are rasters, and what are attribute tables, and how are they linked to the GIS and the different coordinate systems as we've discussed. So spatial databases. A database is a structured collection of data that is organized and stored in a way that allows one to efficiently retrieve, manipulate, and manage the data. I always picture a database as a basket that you can put in the fruits of any kind inside. Now, if you decide to arrange these fruits in a certain manner, you can be able to quickly locate a particular fruit inside the bucket. But if you decide to pour it all in there, shake the bucket, all the fruits will get mixed up. And when you want to pick one, you're not sure how easily you can be able to pick one fruit amongst the other. So let's say you have fruits of apple, mangoes, you have oranges and mixed there. The shape of oranges and apple, they're more or less the same. When you put your hand and you want to pick an apple, you might end up picking an orange because they're all mixed up inside the basket. But if you arrange them in a certain way, and that's what we're meaning, the database has to have data which should be organized. And of course, this is a way of storing that data. So to efficiently be able to retrieve, manipulate, and manage the data, this data inside the database has to be well organized. The GIS database stores information about the location. We've talked a lot about location information yesterday, but also it stores information about the shape of the data, the size of the data, as well as the characteristics or the attributes of that data. So this data may include things like, which we know, the roads, the rivers, the buildings, and also the land parcels or the land use, land cover data sets. It could also be data about the stores. It could be also data just about shopping malls. It could be data about the households that are in the villages, the schools, and so forth. So the GIS database use specialized software and data model that enable the integration and manipulation of geographic data with other type of data such as the demographic and environmental data. So don't think of GIS database as something so unique. GIS database is a specialized software, okay? It's basically a specialized software which you can use to, first of all, input or acquire the data, but also be able to retrieve the data, be able to manipulate the data, and be able to manage this data. Now, if you recall the definition of what GIS is already as defined as a tool or a system that is used for capturing, that is used for manipulating, storing, and visualizing data. You realize that the system of a GIS, a database, is part of that system. And that's why It can be able to help you capture that data. And also that's why it's known as a specialized software. Okay. Now this data in a database can be modeled, and when it is modeled, it can be integrated and manipulated to be able to help in the visualization of demographic or environmental information. I mentioned to you the other day that data is something that is raw, and unless you've processed it, unless you've done some manipulation against it, it remains something raw. But for you to generate information from the data that is raw, you'll have to manipulate that data. You have to integrate it at some point so that you can be able to extract information, which is basically converting data, which is raw, to information. Now, there are quite a number of different spatial databases available out there. One is a file-based geodatabase, and in most cases, this is what we have used. So in your computer, you have what we call files or folders. Folders are simply things that you can have in your computer to store your data. And most of us, for those who have tried to use GIS up to this point, you probably have realized that you have a file, a folder in your computer, which you've gotten data sets of the roads, administrative boundaries, data sets of the schools, data sets of any kind that you have in your computer. And normally what we do is we store this data in the folder. So this is more like a file-based geo database. So it's based on individual files that contain geographic data, and each file represents a specific type of data, which could include the roads, like I mentioned, land use or elevation. In this case, could be topography, slope, and so forth. Now, what is important for you to note is that file-based GIS database, the file-based GIS database are simple to use and do not require advanced software or hardware. And that's why we're trying to say that if you have your data that is stored in a folder, anything, any computer can be able to open this folder and you can be able to look at the data. You may not be able to visualize it geographically, but you'll be able to see the content of what is available inside that file folder. Now, one advanced step is what we call the relational databases or relational GIS database. So this type of database it's based on what we call relational database management system. So a relational database management system, like we have mentioned earlier, is just a software, okay? And this software allows for data to be stored with relationship amongst the data. If you store schools, if you store data on schools, data on hospitals, data on roads in your folder, there's no relationship between the school file, shapefile, for example. There's no relationship between the shapefile of the roads with the schools if it is stored in the folder. They're all standalone files. But if you put it in a relational database, there is that relationship that must be generated between them. This is a little bit of advanced courses we shall be handling in the next segment of courses. But basically, if you've heard of some of these technologies like Oracle SQL Server, MySQL. Okay, these are examples of technologies or softwares that perform relational database applications. Now, what is important is that a relational GIS database uses tables, okay? It uses tables to store geographic data, okay? They're using tables, they're not using objects. And we shall look at the ones that use this object in the next segment. To store geographic data and allows for advanced querying and analysis, okay? So, for example, if you use a folder as the storage of your data, then first of all, this data, there is no relationship between the files that are inside this folder. So you can do advanced analysis, but it won't be to an extent that you can be able to do if it is stored in a relational database. Also, one of the caveats of using a file-based geodatabase is that when it belongs to a computer, one person can access and use it at a unit time. You've seen, for example, if you have QGIS open, and I'm talking to, this goes to those who have tested to use GIS so far practically. If you have one shapefile open in one QGIS application, and then you open another application of ArcMap, let's say, and then you're trying to edit this file, yet it is opened in another folder, then you can't be able to edit it. If it is already open in QGIS and then you open it in ArcMap, yes, you'll be able to open it, but then you can't manipulate, you can't edit it from ArcMap because the file is going to warn you that no, this file has been opened in another application. So in that case, you can't do advanced queries and analysis or editing of the data. But if it is in a relational geodatabase, the software configures it in such a way that when you're editing, it will accept the editing. It's only when you're going to save that the other person is not also editing. So it will allow that small time difference. The moment I click save, and then also my colleague clicks saves, even though it is 2 seconds difference, it will still accept. The final edited file will be saved based on the person who has saved it last. So that's the beauty about the relational geodatabase. Feel free to put up your hand in case you have a question, then I can open the mic for people to share some of the questions they have. The third one is what we call object-oriented geodatabase. So object-oriented geodatabase, this is a type of a database that is based on object-oriented programming. Now, this is probably something so abstract for you to pick, but basically we looked at that yesterday. We looked at object-based data model, and we saw the example of the catchment, subbasins, streamnets, as well as the PowerPoints. So databases that can be able to save data that is object-based model data are called object-oriented GIS databases. So basically they are designed to store complex spatial objects. So in this case, we are not talking about just tables, we are talking about spatial objects. So the word object is very key here. If you're looking at relational database, then you're looking at tables, okay? But when you're looking at object-oriented databases, then your focus is on objects, okay? So object-oriented GIS databases are often used in advanced spatial analysis applications. So for example, QGIS application or software is used, works or operates, or ArcMap, for example, operates based on, or the way the geodatabase is implemented, and we're going to look at that later, is based on the object-oriented databases within the GIS. So for example, if you use Excel, Excel can be able to even generate maps, but Excel is not an advanced geospatial analysis software. So it may not be able to handle data that has been stored in object-oriented databases. Some people are trying to learn how to use the drawing tool, so they're distracting us. So kindly try to probably have a pen and a book on your side so that you'll be noting some of the things I am doing. Now, there is just some segment here that I've put something on spatial database. All these things that we're talking about are all spatial databases. But I just wanted to highlight something here to say that this type of a database is specifically designed for spatial storage. So all these databases can be used to store non-spatial data as well. But if you decide to upgrade the technology to handle the spatial data, normally the manufacturers or the designers of these databases create what we call the plugins, okay? They create a plugin, like for example, the Postgres SQL geodatabase has a plugin called PostGIS. So PostGIS is just an added extension of Postgres, but Postgres can also be used for manipulating or storing data that is non-spatial in nature. So the moment you're going to work with the spatial data, then you must install the extension called PostGIS into your database. So Postgres is a relational as well as the object-oriented databases. Of course, we have some databases that are either relational or object-oriented. And then there are those databases that we use, especially in GIS, like geodatabase, which is strictly or solely spatial, is a combination of relational as well as object-oriented. So just building a geodatabase, there's just a lot that takes us through the process of building a geodatabase, which I wanted to put more, but I realized it's going to be too complex for us to explain. But quickly, what you do when you're going to build a geodatabase or build a database, a GIS-based database, all you do is you first get your data, make sure that all your data has been entered, okay? And then two is you create this database within the software. In most of these GIS softwares, it's just a click, okay? Just click, right click, create a database, and it will have created a database. It will go through a number of processes to make sure that your database has ability to do both. One, it can create tables for relational databases and also create objects for object-oriented databases. So spatial data entry and editing are frequently activities that many GIS users do. So a large number of coordinates is needed to represent features in a GIS, and each coordinate value must be entered into a GIS database. So this picture here is showing a very common, probably most people have used databases. So it's based on the ArcGIS or S3 technology. So they call it a geodatabase. It's not a universal database. It's only specialized for ArcGIS softwares. But why I use it, or why we have used it, is because it gives a very good highlight of how the databases are arranged. Like I mentioned, they try to make sure that these databases can be able to satisfy the interests of a single user, but also for a multiple or multi-users. So single user is just an individual. Multi-users is, it could be for a big organization or ministry as a whole. So for single users, you can have a file geodatabase. Like I mentioned, you have a folder and you just put things in there, or you can have what we call the personal geodatabase. Now, a file geodatabase in terms of ArcGIS is more advanced than a personal geodatabase, but they are all for single user base. Okay. Now, for multiple users, you need to have a relational database management system software. Okay, RD, BMS, meaning a relational database management system. So through that, like we talked about it earlier, it allows you to be able to, for multiple users to access the same data, and they can also be able to edit it at the same time. This computer or the software or the system will be able to keep track of who is editing where and who is doing what. And then when you save, your saving or what you've saved will be captured. And then the moment another person also saves, their edits will also be captured. Now, then later, it's going to give you an opportunity to merge, okay? To merge the edits from two different people. It could be even more than 3 different people. But also it goes ahead to save the information regarding what each individual was working on or editing. So, and that's why it's a multi-user geodatabase. It has one big layer here of what we call the relational database management system. So aspects like enterprise geodatabase, working group geodatabase, and then also just the normal desktop geodatabase are part of this multi-user geodatabase. Now, what is the capability of a geodatabase? The capability of this geodatabase is that you can be able to store attribute tables, feature classes, cartographic data representation. You can perform annotation, dimension. You can do relationship classes, and then store also the raster data sets. There is also an advanced part of it where you can do raster cataloging. You can handle or perform or execute topology, do geometric networks and network data sets. It can store terrain and locator service data. Also survey data, which is probably a card, okay? And also the different toolbox that it can handle. So relational geodatabase basically is one of the most favorite geodatabases that you can use. The technology is really, really good. And most of the softwares, including QGIS, has been built using this concept in mind. But in summary, basically a spatial database is like a basket, or it could be like a paper bag that you have a number of things you want to store inside there. But you must store or put them inside this paper bag in an organized structural way so that when you want to access it, you can easily access what you want. I'll give you an example of your kitchen. If you have a kitchen and you have a number of things that is in the kitchen and you just disorganize them in any way. I'll give an example of gentlemen who have stockings. If you have stockings, maybe 4 to 5 pairs or 10 pairs, and then you just mix them in the basket. I am telling you, when you wake up in the morning and you want to take one of the stocking or you want to put on your stockings, you'll have to keep looking for the pair. Okay, so you pick the first one, you pick the second one, the pair is the wrong one. You pick the third one, it's a wrong pair. So just imagine you'll spend over 10 minutes figuring out the pair of the stocking. But if you decide to tie them together in an organized way, you tie the stockings that are the same together, it becomes very easy. You just pick one and they're all tied. So in other words, you've organized your stockings in the basket, the laundry basket that you have probably at home there. And just in the kitchen, you need to know where you pick the knives, the cutleries, where maybe the plates. In our home, we used to have a cabin, yeah, where the plates for the visitors were placed, and then the plates for the normal family members are placed, and then the cups and all that. So if you have your cabin and then you organize it in a way that you know where things are, you know where to pick things up, then it becomes very easy for you to retrieve that product in case you want it. So databases are very advanced, and maybe what I'm going to do, I'll pick a video and post it on the platform, just for those who want to spend a little bit of time, they can look at it in advance. It's very hard to explain just things about the databases other than doing them. And that's why I decided that we discussed that we push it to the next hands-on training where we shall be handling issues of databases, where you create them, start populating them with the data, and then see how do you retrieve the data from them, how do you join the different data sets that are inside there, so forth. Nonetheless, let's go to the next part of this training. So here we are going to be looking at the spatial data analysis. This is a big topic that all the GIS practitioners ends up doing. So after you've gone to the field, you've picked your data in any way you picked it, either using a mobile phone, you picked it using a paper form, you picked it. You'll be able to organize this data. If it is in a digital format, you just do a little bit of cleaning and all that. If it is a paper format, then you'll have to enter this data and make it digital. So in most cases, we use an Excel or any Microsoft platform. But of course, people now have advanced platforms, for example, the Kobo Collect or the Kobo Toolbox, or you can also use ODK and all these initiatives that are out there. So most probably you will have your data in a digital format already. So then you need to put it in GIS. Of course, if you've used, for example, it's possible for you to use platforms like Survey 123 for the GIS, ArcGIS environment people. but also you can use there's application in QGIS that you can also use for capturing the data from your mobile device and so forth. So when you bring it in a GIS, there's certain things that you will have to do to capture it into the GIS. I'm not going to talk more about that, but basically here what we want to say is that after this data has been entered into the GIS, you now want to start manipulating it. And that process is spatial data analysis. So this analysis is the process of analyzing the data that is tied into a physical location or geographical area. This type of analysis can help reveal patterns, okay? You can reveal patterns, you can reveal relationships, okay, that are not immediately apparent in a non-spatial data. So this analysis, this data may include things like the maps. It could be satellite data or imagery, a GPS coordinate, or any other data sets that are tied to demographic data, economic data, for example, the GDP, the environmental data, climate data, and so forth, can be manipulated using the GIS. And your interest could be, or in most cases is, you want to look at patterns that are in the data and also the relationships that are inside the data. Spatial data analysis can be used in a variety of fields, okay? It could also be professions in this case. For example, urban planners use or run spatial analysis. People who are in the transport industry, those who are in environment management, and then those that are in the health sector also use GIS analysis. So it can be used to identify areas of high risk. We shall look at the detailed applications of GIS. You can look at vulnerability for those who are performing hazard analysis. For those who are doing marketing and all those business, you can do optimize resource allocation, and then assets impact policy decisions on different populations can also be performed with the GIS analysis. So there are a variety of techniques that one can use to perform this kind of analysis, and it could include spatial statistics, okay? It could be spatial modeling. It could also be spatial visualization, okay? For example, if you're making a very interesting maps, and we are going to look at some of those tricks that you use to visualize data in a very informative way. So these techniques help us to uncover the spatial patterns and relationship, just like I mentioned earlier, that can inform decision-making and policy development. Now, I've not talked a lot about this key aspect, decision-making and policy development. But what you need to know is that every spatial analysis you're performing, either you want to guide decision-making or you want to help implementation during the implementation of a certain policy. So make sure that accuracy is very key in what you're producing, because at the end of the day, when a policy has been developed and implemented, when a decision has been made, either it will affect the human life, their social livelihoods, but also the environment as a whole. So make sure that the products that you generate are genuine products, okay? GIS, you can decide, like yesterday we talked about generalization. You can decide to exaggerate things, okay? For example, you can decide to exaggerate the pollution levels in the country. You can decide, a colleague of mine was telling me about how the map of United States of America is not necessarily as big as it is supposed to be, but because they wanted to influence the superpower aspect in the mindset of people, I decided to make the map of the North America bigger. And then people now think the US is bigger. And this, you can manipulate data within the GIS using the generalization techniques to communicate different information. Let's say, for example, you could, if your interest is to influence maybe environmental policy, sort of enaction or development, you can decide to draw a forest area. You can decide to draw a map of a protected area, and you indicate very high attractive colors of, let's say, red, showing danger that is happening inside the protected area. And just because you've decided to use that particular color, it will communicate a very strong information to the decision makers, and that's the policy development. So you need to be very careful what you're trying to develop, and you don't have to be biased. You need to be as much objective as possible. And also, the accuracy should be very, very key. Don't generate for us the map just because we don't know how the map actually look like, and then you lie to us with a different map or things that have been exaggerated at the end of the day. Now, selection and classification is one of the ways that we can perform analysis of any sort. So selection operations identify features that meet one to several conditions. So we can perform different kind of selections. Like, for example, if you want a certain age group in the census data, you can do a selection and say any person who is 60 years and above is what should be selected. So you can do that. So the simplest form of selection is the on-screen query, like I've just mentioned. You just run a query and then you can be able to obtain certain information. We have done this a lot in Excel, either by a search, you just search for a certain criteria in your Excel file, and then it will give you information. In a GIS, of course, it's a little bit more advanced. It gives you ability to do what we call structured selection. So this selection is where you're using a query language to perform the selection. So a data layer is displayed and the features are selected by a human operator. Okay. Now, the operator uses a point device to locate a cursor over a feature of interest and sends the command to select, then via mouse click or a keyboard entry. Just like I've mentioned, you can click things to select them using your mouse, or you could also just use a cursor to move around things and select them. If, for example, I move this cursor from left to right, I will be selecting those particular words. But in the GIS, you can just use a mouse to click, or your touchpad in your laptop to touch, to click on things, and then it will be able to be selected. So queries may also be specified by applying conditions solely to a spatial component of spatial data. These selections are often based on the attribute data table for the layer. Now, some of these things are very abstract if we're just talking about them. But at the end of the day, what you're doing, you can do a selection based on the attribute information, or you can do a selection based on the spatial data that is available in the map. So if the attribute match the condition, they are selected. If the attribute fails to match the condition, they are placed in the unselected sets. So if we are doing this manually or hands-on, this would have been very easy for you to comprehend. But the picture on the left is talking about what we shall look at later in details. It's talking about the classification aspect. Now, the classification we're looking at is manipulating the data without changing the background, without changing this actual data, but you're just manipulating the data for visualization purposes. So you do a classification on the data. So in most of the softwares that use GIS, you can do what we call natural breaks. So the natural break, we shall look at those in details. How do they operate and why do they show data the way they do? We can also use what we call the equal interval. So how do equal intervals operate? And if you look at it keenly, you take time to look at the legend, you'll see how different things are operating. So this is all data about shelter. And probably it's just talking about it's just talking about, so this data is from the Statistics of Canada this year. And I didn't pick the actual subject of why they were developing this, but I just wanted to highlight to you that there are 4 different types of classifications that are used. One is the natural breaks, the equal intervals, the standard deviation, and the manual breaks. So you'll be able to see in the legend how each of these vary from one classification to another. What you need to see is that if I perform a natural break classification, the things that are in dark red and things that are in yellow, how do they correspond when I've done unequal intervals? So you'll probably see that this is natural breaks will tend to over exaggerate the different quantities in the file. But also if you look at the legend alone, to be able to tell you the different classes that have been selected there. So let's dive more into selection. One way of doing a selection is by using a set algebra. I'm not taking you back to high school again of this mathematics, but just to highlight what we're talking about here is that this selection conditions are often formalized using set algebra. So what are the set algebra? So set algebra are operations such as less than, greater than, equal to, or not equal to. These selection conditions may also be applied either alone or in a combination of features that are being selected. We'll give an example here. You have the state entry north of Arkansas, something like that. So the actual place in this area is here, and it's shown in this map. So in the first selection, you interested in just looking at what is above the states that are north of Arkansas. So Arkansas is here. Arkansas. Okay. I think I'm messing up with my English. Arkansas is the state that is here. So you can do a query and say, I want to see anything that is north of it. So that will be the states in the north of it. If I want to say, I want states that are larger than this value of this state of Arkansas, then this will be what will be selected. You can also say, I want things north of it and larger than that. So now you're combining this query, north of it plus this. Now you'll notice that we're using an as an operator here. So when you're using an, it means you're combining two queries into one. So then when you're using or, which I didn't really put here, then you'll be only selecting one query at a time. We'll see that in details, probably in some other slides ahead. Now you can do, we're still looking at the spatial queries. Spatial queries, we're looking at it by the fact that we are working with the geographic data. Later, we shall see how you do a query on the attribute table. So for the case of the spatial selection operation, still, you can use what we call adjacency. So adjacency selection operations are used to identify those features that touch. Okay. So you remember we talked about spatial relationships last time. So there are things that touch other features. These features are typically considered to touch when they share a boundary as when two polygons share the edge. So you do say, okay, this is the area of my interest, okay? And I want any other feature that touch this area, and then they will be selected, okay? Now, you can say an adjacency that share line required or share node or line that is required. So that would be the differences between the two adjacencies, one that shares a line and one that shares a node. Okay. So next, we want to look at another one here. This is more or less, we're trying to run in a lengthy part of the query to look at how the different, if you're using different layers to run a query, what do you get and how does it look like in the attribute table? So one we have, so we wish to identify counties with a hazardous material site. And this site is in the upper left that contains, so here, these are the hazardous sites that contain part of the river. So here, what we're trying to do is to say, okay, we have these sites based on the country, and this is the level of hazards they have. And then here we have also the watersheds, and these watersheds also have the rivers crossing through. So what is going to happen is that when you overlay the river and the hazards, the polygons that are touched by the river get selected. So we first apply a spatial selection on counties with the watershed. So we're first doing only this one. We're first doing this selection. We're saying, okay, watershed plus counties. So we only pick those counties that are within the river watershed. And then next, what we do, then a table selection on coincides the country to identify those with that. So next, then you say, okay, the product of this, which is this one. Okay. So the product is here. So then we say now this plus this, then we shall get the counties that are first of all having the river passing through, but also have this hazard within them. So how are we doing this? Physically, basically you have the county data or administrative boundaries of the hazmat sites. And then you have the river together with the watershed. So you perform a selection. So when we are doing this and this, we're just running selection. And then the product is later counties with AMZAD sites are generated. And then we say, okay, anything, we're now running some bit of algebra here that one, if the hazmat is greater than 0 in terms of the hazard. If the hazard is greater than 0, then select it. If it is not, then make it a 0. So in other words, anything that don't intersect with these sites will be eliminated, and anything that intersect with the sites will be considered. So those are some kind of complex selections that you can do. Now, in this case, we have 3 layers. We have the first layer here, which is the hazard sites. And then the second one here, we have the watersheds. Okay. And within the watershed, it has the river and all that. And then we have the third, data sets. And what we're doing is we want to see, based on these 3 sites, we want to obtain the counties that have, first of all, the river passing through them, but also have this effect, so that we can make a decision and say, you know, the cleanup of the hazard must be performed in these counties and not in all the counties of interest, okay, that we have. So I'll give an example, like when COVID outbreak was in the country, or in our countries, let me say that, you'll find that you could not do an intervention in all the districts in the country. So you needed to first overlay the cases of COVID onto the district boundaries of your country. Others have maybe the different ways of, others have states, others have counties, like in the Kenya. So you need to overlay the COVID cases with the counties, because you can't make an outreach to all, put emergency centers in all the districts or in all the counties. So you need to first narrow down that selection. So this is basically a typical example of what you can apply this kind of selection on. So we are going to go further and look at aspects of classification. So classification, as I mentioned, is a spatial data operation that is often used in conjunction with a selection. A classification, also known as a reclassification. So there is an extra term here, a reclassification, which also means recording. Okay, so if you've already recorded the data and you want to record it again, then you can be able to perform what we also call a reclassification on the data. So this will categorize geographic objects based on a set of conditions. So you'll have conditions that you'll set, and then the geographic objects will be set based on that. Classifications may add to or modify the attribute table for each geographic objects. And this modification of the attribute table may in turn be used in further analysis. And this analysis will be more complex because they are based on a combination of an additional classification. So let's look at the land parcels. And these land parcels have been reclassified, okay? So initially, maybe the land parcels, if you map them as a feature data, they all have the same gray, okay? The color is all gray, or it is white, or it is hollow. But later when you run a reclassification on it, you'll be able to have it colored differently. So we have white here, we have sort of gray, and we have a little bit of darkness or darker gray here. So things that are in dark gray are large, things that are in slight light gray are mid, and things that are in white are small. So that's just a simple way of generating data for visualization purposes only, but without changing the information, underlying information on it in the attribute table. So like when you perform this kind of reclassification, you're actually not modifying the underlying data, but you're just generating a visualization output of that data. Excuse me a bit. So as I take a glass of water, I want to look at some of the questions that are in the chat. Okay. Okay. Abdi, you're saying, do I need to write the range on the table as I have done my classification? Yes, Abdi, if you want to create a permanent file based on your classification, then you can write that range into the attribute table. But when you're going to perform a reclassification, depending on the method you'll choose, I've just showed you three: natural break, equal area, standard deviation, and I don't recall the last one. The computer will first give you the outputs, and then based on the outputs, you can then do what we call a reclassification if you want to permanently save those classification in your output. Okay. I hope I've answered you. Anyone with a burning question again? So from the legend on the shelter map statistics, does the 4K lie in low or medium? Okay, let me just go back there and look at what you mean. Okay, so Priscilla is saying, from the legend on the shelter map statistic, does 4K lie in the low or medium? So 4K. So depending on remember in the natural break classification, the computer is classifying the data based on the natural look of the data. That's where the natural breaks come from. So for example, if you have data that you have a list of data that is from 10 to 100, and then suddenly it jumps to 1,000 to maybe 10,000, okay? Then it again jumps from 10,000 to 100,000. So if there are those clear breaks between your data sets, the natural break classification is going to break the data based on those leaps, those clear jumps between your data values. So you need to know that, okay, how does my data look like? But also you need to know how is the range between my data? Is it a clear, is it a direct or a smooth range between my data? When I mean smooth, data starts from 1, 2, 3, 4, 5, 6 up to 100, and that's it. But if you have data, others are in thousands, others are in 100,000s, others are in millions. So there's always that break between moving from tens to hundreds to thousands to millions. So the natural break will be created based on those leap gap between your records of the data. Now, sometimes you need to know what an equal interval is, because what the equal interval is basically doing here is saying for each of these classes in the legend, the records between them are the same. So if you have selected your interval to be 10, then it will try to say all 10 records should be in one class. So this will have 10 records. This one will also have 10 records, 10 records, 10 records, 10 records. But remember the values for the records vary, and that's why you have the different levels in your data. For standard deviation, what it's going to do, it's going to first calculate the standard deviation in your data. So standard deviation is that value minus the mean divided by what? I don't remember. So it looks at the differences between your mean and the actual data. If the deviation is maybe, let's say, is ranging between 1, 2, 3 to 10, then it will arrange the data based on the standard deviation. So what I mean here is that it's not actually using the actual records of the data, but it's first creating the standard deviation of them and then mapping them or classifying them like the way you're seeing it right here. Manual breaks, if you understand your data very well, then you can manually break them. You can manually say, my data is in tens, hundreds, thousands, and millions, or 100,000s. So what you'll do, you'll say, okay, any record that is between 1 to 100 will be in that class, number 1. Data that is between 100 and 1,000 are going to be in the second class. The data that is between 1,000 and 10,000 will be in that class. The data that is between 10,000 and 100,000 will also be in that class, like that. So you can manually break the data that you have. Mato, I didn't want to turn on the chat, but let me do that so that we can listen to you, Mato. Please go ahead.
Sorry, I will take us a little bit back. When you showed the slide with the selection of all the places north of Arkansas, I noticed that some of the boxes were not selected. Well, could there be a reason for that?
Just give me more explain more statement, because I'm not speak to you very well.
Okay, so for example, the polygon right above the Arkansas in the selection that select all states north of Arkansas was not selected. I just want to
Yeah.
understand what could be the reason for, despite it being north of Arkansas, but it still wasn't selected.
So for example, you mentioning like Los Angeles and so forth, this other polygons on the extreme left, you mean?
There is one right above the Arkansas, and then there is other one.
Like this one here. So this could probably be not, it could be part of maybe a river or something like that. I'm not an expert of the US map. Maybe Dr. Since he did his PhD from there, maybe he can chip in and tell me if this is also a state of its own, or it could be just um, maybe a district or a small admin boundary, or it's just a water body or something like that.
Okay, thank you.
Yeah.
Which one is that?
He's asking about this one here.
Which one?
Yeah,
The one
and
I've circled.
there's one above the Arkansas itself. Yeah.
Above. I don't see that.
Arkansas is down.
Yeah, Arkansas is here. Yeah, but he's asking why is this state not selected, the one I've circled?
That's the water body.
That's what I thought
I
as
think
well.
it is one of the Great Lakes.
Okay.
Yes.
Thank you, Doctor. All right. Unless Jen, let me start with, I don't know whether Eunice came before Jen. Eunice, can you come first?
Yeah, thank you very much, Thomas. I'm just following up on that question of I can't remember what name the person who just asked. I think the one you just shaded is not Arkansas, but that is the one that he's asking about. Arkansas is the one that is below what you shaded. But it's the question is that is entirely north of Arkansas. If you see that the southeastern the southeastern tip of the state above that, we still have a point that is not in the north of Arkansas. So it's not entirely, the whole of that state is not entirely north of Arkansas. So that's why it was not shaded. If you see that southeastern tip of the one you had shaded before, there is still a place that is not entirely north of Arkansas.
North, yeah, I can see it actually. It's just right.
Yes, yeah. So that's why it was not shaded. Thank you.
Okay, thank you, Eunice. Jen?
Yes,
Jen,
Doctor,
are you still?
Yes, I'm still on that particular point. It's quite confusing because I'm also wondering why it was not shaded, yet it is directly up, directly in the northern part. And also when you look at these other, okay, that one could be another body, but I thought all these states, as long as they're in the northern part of the city, they should be shaded. So could be there a reason why these other, they are not being shaded?
Yeah, like Eunice has mentioned, there's a very small part of it here that is actually towards the east. So that's why it can't qualify as entirely north. You saw where I've circled?
Yes.
Yeah. But the logic is not that this example is right or wrong. You need to just know that you can do a selection based on this kind of statements. You can say, I want anything above, or I want anything greater, or something less than, or something equal to. That's the most important statement or learning that you need to pick. That in the GIS environment, there come a point whereby you want to just deal with a small set of your data, not entirely the whole data set. And the GIS gives you an ability to perform a selection on that data. So that is what you need to know. And you need to know, how does this operators, how does this algebra sets work? How does, how do you, at what point do you need to write what? That is the most important information that you need to pick from this. Thank you so much for that contribution from you people. I'm grateful. Let me check the chat if there's still somebody saying. Okay, Dr. Brian Makabai is my neighbor, but I can't pronounce his name. I think it depends on the data in the database. They may have allocate that state to the east and not the north. Yes. So in the attribute table, yes, Brian, you've actually said it well. So this kind of query that was being performed is an attribute based query. Okay. So in the attribute table, you'll have the field. Let's say I have state A, state B, state C. Now, then there could be an area called position, okay? Position, and this would be north, this would be east, and this would be south, okay? So they performed the query based on this field and said anything that is in the north. So that means but for some reason, this state is being given a value east, then it cannot be north. So that's why it was not selected for that reason. That could be probably the reason why it wasn't selected. They didn't do a selection based on the spatial selection, okay? Even you'll see this query that they're saying a state that is larger than 400 square kilometers. These are attribute field. So for example, they could be having in the attribute table a column or a field that is area. So for each of the states A, B, C, D, there's a column or a field that is specifying the area. And you'll see that anything that is greater than this value will be selected. Okay, so all these kind of queries that are being performed here are based on the attribute query, not the spatial query. However, in the second one, the query is based on the spatial query. When it comes to Abdi saying, when it comes to algebra set, can I perform combination more than two? Absolutely, I should have answered you already. Yes, you can do more than one set of algebra or operators. You can use more than one operator in your query. What comparison can spatial data collected in a field used to show different features using algebra? So, for example, when you collect a GPS point, let's say you're going to collect GPS points for buildings, okay? And when you collect these points, you'll have in your Excel, when you're entering, you're going to enter, first of all, X, and Y coordinates. Okay. So building A, building B, building C, building D. All right. So all of them have the X and the Y, which is the GPS point. So these two are just the GPS points. Okay. GPS. Forgive my drawings. I'm using a mouse to do that. So this is only GPS information. But in addition, you can say, okay, what is this building type? Okay. The type of the building in your Excel. Now, when you're entering, you can collect this using the ODK form or survey form, or you can collect it using a paper form, whatever you want to use. So the type could be maybe residential, it could be commercial, it could be a factory, and so forth. And all these questions you people are asking are based on the databases, which I have not dwelled much on. And I see why you're asking, because you want to understand. So because of the type, you could also have another field called area square meters. It could be 2 square meters. It could be square, maybe kilometers. I don't know, any value that you feel like. It could also be, this one could also be 4 square feet or something like that. So these are all the query on this X and Y's. So remember, when you plot this, it's going to be a point, okay? Spatially, they'll be looking points, but underlining these points, there's an attribute table about each of them, okay? So each of these has the attribute table that is linked to every point that you have. So you can perform a query and you can, for example, say, I want all the buildings that have the type residential plus their 10 square kilometers and above, or 10 square feet and above. Okay. Brian Makabai is a surveyor, so don't kill me with my units of measure that I'm bringing here. Yeah. But basically, you can do a query based on this column and this column, a combination of them. But also you can just do a query based on a single column and say, I'm only interested in the type of the buildings only. Okay. Now, like I mentioned, the moment your interest is to do a query based on 2 columns, then you must use an operator. And if you're doing a query based on only a single field or column, then you use an operator called OR. So for example, you can say, I want a building which is type residential, or it is a factory. So in that case, the result that you get will be those buildings that are residential plus those buildings that are factory. When you use the AND, it is something different. The result of a AND is just 1. The output is just 1. Because first of all, you're saying, I want the buildings that are of type R, and on top of them being type R, they must be having an area that is 10 square feet and above. So in other words, in this case, the output is only 1 feature. Okay. For the O, the output is going to be 2, types of features, two feature types, okay? The first feature type will be those that are residential, and the second feature type are those that are factory, okay? So these things can be handled very well practically if we were doing a practical session. It would be more clear for you to understand. But all you need to know is that you can use a combination of these operators to run this. You can also combine a or and a and, okay, in your query. All you need to know is you need to go ahead, validate your query, and first of all, be sure that your query is correct. But also you need to know what you're doing, okay? All right. Stephen Ochen, you still kept your phone Techno, so maybe you're using two accounts, so you want them to look different. That's okay. So the query order was for state entirely north of that. Okay, thank you. You're just trying to respond to the questions. Okay. So let's continue. So still more about classification. So a classification may be viewed as an assignment of features from an existing set of classes to a new set of classes. Okay. So when you're doing a classification, yes, you'll probably be able to generate an output for visualization purposes. But just like somebody mentioned, you can actually go ahead and save this legend inside your attribute table. So in this case, you'll have generated a new set of data totally. But normally, the beginning part of a classification is for visualization purposes. You want to just have a visualization of the classes you have. But later, if you're interested in saving it permanently in another layer file, then it can be saved permanently. So the assignment from input attribute table to a new class value may be defined manually, or assignment may be defined automatically. So like I mentioned in different classification types, like natural breaks, equal area, standard deviation, and the manual one, you realize that you can, the other three, you're just doing it, the computer is performing that automatically based on what you give it to do. But in the manual classification, then you are doing it manually. So for example, here, a human analyst specifies in, okay? The in is this column or the field. So this is the in column. So you specify the in items for the source data layer via classification table, as well as the corresponding output value for the in variable out values. So here you're doing it manually and you're saying anything that is A should be 1. Anything that is B should be 1. Anything that is E should be 2. Anything that is 1, I rather, should be 2, should be 3. So through that, you'll have the table, or your geographic data will cease to look like this, and now it is going to look like that. So instead of A, you have a 1. Instead of B, you have still a 1. Remember, you've said A and B are 1. And then C, or rather E, is going to be a 2. So anything that is 2 and 2 must be 2 and 2. E becomes 2, 2. And I this time become 3. So normally, Right, there was a bit of internet just glitch a bit. I had to change it. Okay, we shall have a break shortly. Juliet is going to guide us on that. So still talking about the classification, we can also do what we call the binary classification. Remember, what we were doing here was a manual-based classification, but also we can do a binary classification. And every time you're talking about something binary, you're talking about a 0 and a 1, which can also be a true or a false. It can also be an A or a B, okay? So there are just two parts of what you're doing the classification, okay? So this is perhaps the simplest form of classification. So the binary classification places objects into two classes, a 0, a 1, and that. So for example, that we're seeing here, classification of binary features are placed in two classes in a binary classification, west and east. In this case, the west is going to be 1 of something, and the east is going to be a 0 of, in this case, would be a Mississippi river. So we are saying, okay, in case this river is passing here, okay, anything that is in the west will be, anything that is in the west will be a 1, and anything that is in the east is going to be a 0. So later you can then record this information in your classification table and make it permanent so that this file will be permanently saved with a value of 1 and a 0. A number of these reclassifications are done when you're doing site suitability analysis. These are more advanced sort of analysis that you're performing. So it's the one-step process towards generating a site suitability analysis. I'll give an example, like if you want to generate population density or demographic data for your districts in the country. So what you're going to say, okay, I want those districts with females above this age and those districts with female below this age. You could also say, okay, I want to generate the admin boundaries showing population density for only male, okay? And then only showing that for only female. So a true and false, or a 1 or a 0, A and a B, male and female, could be examples of binary-based classification. It could also go to the religious aspect where you say, I want to map Islam versus Christianity or something like that. So those are binary sort of classification that you will be performing. So let's understand some of these classifications that we looked at earlier, and maybe try to understand the concept and what is really going on. So the two that we have looked at are more of the manual-based classification, where you are assigning the values based on what you want. But here is where you're doing an automated classification process. Now, before I go to this, I think we are almost time for the break. It's going to be a little bit technical, so I want to handle it after the break when people have refreshed a little bit. So kindly to you, Juliet, to guide us on the break. All right. So welcome back from the break. I hope you took some refreshment, you've refreshed yourself, and that you're ready to hit another road for the next step. We still have quite a number of things to cover, but absolutely today we shall be done with GIS, and then tomorrow we start on the remote sensing. We shall also agree on the Friday session because we have realized we still have a lot to cover. So we'll agree on Friday because it's a public holiday. But as for us who are here, we'll try and discuss and see, is it possible to have a session maybe for a few hours, and then people can go out for their holiday. So that's what we shall agree on unanimously as a group. All right, so neighborhood classification. So like I mentioned that earlier, we've spoken a lot on the manual way of doing a classification, but how can you do a classification automatically? So automatically doesn't mean that you just click and then the computer will give you the right thing. You still need to tell it something to do. So teach it, tell it something, how you want things to be done. So an automatic classification uses some rule to specify the input class to output class assignment. The input and the output class boundaries are often based on a set of parameters used to guide class definition. So there's a very important statement here called class definition. Okay, so you need to define your class. And the way you define it is the output that you will see. So we looked at four types earlier, but there's an extended one in terms of the classification types. There's neighborhood, equal interval, area, equal area, and then the natural break. Now, let's start with the neighborhood classification. So you'll probably see an image on our left that is trying to show the counties boundaries, the county boundaries, but also these county boundaries have an underlining information in their attribute called the population. So for these outbid boundaries, we want to classify this, let's say if there were maybe districts or parishes, we want to classify them based on population density that is within it. So the first thing is we need to note that when we're running a neighborhood classification, there are things that are called outliers. Okay. And also the other part is that when you run a classification, there's always something that is created for you in the background, and that is called a histogram. So the histogram tries to depict or show you how the output and how the data has been classified. Classification, sometimes also we call it categorization. So you're trying to categorize your data based on the records that you have. So in total, these polygons are 1,074 of them. And then the population for the neighborhood will range from 0 to 5,133. So in the histogram here, you'll see that this ranges from 0 up to 5,133. Okay. However, within it, we have what we call outliers. So there are about 3 of them. So where are the outliers? The outliers are anything that is greater than 300 and 3,300. So anything that is from this point out is an outlier. Okay. Now you'll see that because there is a point when there's no record shown here, and then suddenly you're seeing some values out there. So a bar graph will show the frequency of the neighborhood population. So here you're running a neighborhood classification approach to categorize your data. So you'll see that the frequency is based on the histogram is about 8. That is the highest frequent numbers in your data. In terms of this, it's the population. It's about 8.1%. And it ranges, it doesn't go beyond this value because these values are outliers. So it ranges between 0 to 3,000 and then also 3,001. Now, what do we mean is there's, of course, here it's just quickly showing you how the data is distributed. For example, I can't tell which value is this and that based on this histogram, but you'll see that it's ranging between 1,500 and below. Now, note that there is a break in the chart between this value and this. So basically what they're meaning is there's a break at this section. So that break is trying to get rid of the outliers that we talked about outside. So that is for neighborhood. So the input and the out class boundaries are often based on a set of parameters that a user will guide to define the boundaries. So somebody will ask me, at what point do we use neighborhood type of classification? So the neighborhood type of classification is normally used when you want to test for the outliers in your data, but also you generally want to classify data based on their neighbors. Okay, you want to classify data based on their neighbors. I'll give you an example. For example, if you have the admin boundaries of the district or of the sub-county, depending on how your administrative boundaries in your country is classified. Now you have maybe a pandemic outbreak, okay? And cases have started being reported from each of those districts, if the districts is what you're using as your default administrative boundaries. So if cases start falling, coming through, now let's say here you have polygon for the administrative boundaries, and these are the boundaries of the districts, like that, like that. Okay. And then for some reason, there is an outbreak of maybe, let's say, cholera, or it could be, people talked a lot about COVID, so I don't want to talk about it. I just want to say maybe there's Ebola outbreak in this sub-county. And then you have, for each of these administrative boundaries, you have population density information regarding them. Now, you want to say, okay, in case we have to run more like a relief program, or we are coming up with a relief project or a surveillance project or initiative. Now you want to run a classification and say, okay, based on where the outbreak is and the population distribution for each of these, I want to run a neighborhood classification to identify, first of all, areas with equal number of population, but also this equal number of population should be neighboring each other. So that's the kind of classification that you can run. And these are quick spatial based analysis that you can perform to visualize the data, but also you can save it as a permanent result if you decide to do what we call a reclassification. If you have any question regarding this, kindly let me know. I'll keep posting them in the chat. I'll keep responding to them. Another form of classification is equal interval, and we need to know the differences between them. So in equal interval classification, the values of the same admin boundaries, which is 500 and 5,133, they are split into equal parts. Now, the equal parts that it is split into is defined by you, okay? And this should be logical. You don't just define the equal parts based on how you want it to be. The equal parts should be defined based on the logical understanding of how your data is distributed. So in most cases, the histogram, first of all, helps to show you how your data is distributed. Is it normally distributed? And for some reason, you might have to normalize your distribution of the data, maybe using a histogram or standard deviation calculation on your data. Okay. Yes. And Mercy, this is what I'm trying to explain, that you can understand the population structure or break in your data based on the histogram. The histogram helps to tell you how it is distributed. For example, for each of these polygons you're seeing in here, polygons that have a population density of, let's say, 1,000 in this range, it could be here between 1,000, between 0 and 1,000. This is how the structure is. Okay, so between 1,000 and 0, this is how the population density is structured for each of these polygons. So, for example, you'll see that this value, which could be 3,000, maybe 400 or 4,000 in this case, is these polygons. Okay. Of course, we have another one here, which is an extreme. It's just that the color is black and white, but this could have a more deeper black. Okay. It could be having a more deeper black because the population density is over 5,000. So it could be linked to that. But all you need to know is that each of these polygons have the population value. Now, this histogram is just explaining to us how the population inside these polygons are distributed. Now, it doesn't really tell you exactly that this bar is linked to this. This one is linked to that. This one is linked to that. No, it's trying to generalize the whole record. If you want to study each polygon separately, then you can run a selection that we did earlier. You can say, I want to see a county or a district that is having this kind of population, and you can be exact so that the selection will be performed for each of the districts that you have. But this tries to summarize and generalize all the values within based on the classification type that you will have decided to use. But how is natural or neighborhood classification different from equal interval classification? So what the equal interval classification does is that it generates, first of all, it tends to say, okay, the interval between 0 and the next one, or between this value, should be the same. So for example, if you say 0 to this, the interval there is, let's say, it's 1,701.11. Yeah. Now the interval between 1,712 and this is also the same. Remember, you said equal interval, so the interval here will also be the same. It's also going to be 1,711. If you subtract this from this, you'll realize that the value is also 1,711. So this is the concept of making sure that each of the class, here we have class 1, class 2, and class 3, have the same number of records inside them. So what this is doing is saying, okay, how many polygons are here? There are 5,133. So I want to divide them into 3, okay? And say 5,133 divided by 3 is this value. So that means each class will have those number of polygons attached to them. And then what it's going to do automatically, remember this is an automatic way of doing a classification. It's going to now place the population density based on the range. So what it's going to do, it's going to say, okay, if
Oh
they
my
are,
God. Woo. Oh my God.
okay, I don't know what was going on there. I'm going to give Aisha and I see some chats coming, an opportunity to ask questions. So in other words, what it's trying to do is that if I split this 5,133 polygons into 3 classes, which is 1, 2, 3, then I say for all those 1,711 polygons, the ones that have a value from maybe a certain range, in this case, it has done it in the histogram. So let's understand it very well from the histogram here. So what it's doing here is that it has split it into 3. First segment there, then you have another segment there. Okay, so this is the class 1. So all the polygons that fall within a population of 0 to, let's say, 3,000 something are going to be under class 1. So these are the classes here. Then the range, those that fall between 1,800 to 3,000, maybe 500 or 4,000, this range, these ones are going to be in class number 2. And then anything above it in this range, these ones are going to be in class number 3. And class number 2 will be having this kind of color, and class number 3 will be having that kind of color. Okay, so that is equal interval classification. Now, the issue here is that you are using the total sum of the records, or rather the total sum of the spatial objects in your data, and in this case it is administrative boundary, to decide how to split the data. Now, splitting is what we call classification. So you're saying, based on the total number, I want to classify this data into 3 classes. If you had decided that, you know what, this number 5,000, which is the total number of the admin boundaries, I can decide to split it into 4. So you divide it by 4. So in this case, you're going to have another extra class here, and then it will also have, so these values will change. So that value divide by, I can't figure it out very well. Divide by 4 might be about, it's still going to be about 1,000, maybe 500. So the value will be ranging from 0 to 500 to 1,500 and 1,600 to like that. So you'll have more ranges here. So depending on how you really want to classify or split your data. So let me look at the chart first, and then I'll allow Aisha to talk. So Jen is saying, when one collects data and finds an outlier and goes ahead to analyze that data, won't it affect the results? So an outlier is something that is good in a sense that it will first of all tell you if your focus is really to see areas that are having some uniqueness in them, then outliers can help you identify them quickly. Now, if you're using an outlier, if you're using the whole data record as a basis to make a decision, and yet you have outliers in them, then they are going to affect your results, okay? In this case, for example, using the mean, which has an outlier, might affect your results because they are extremities. So then you decide to go with a different statistical way of making the decision. For example, you can decide to go with the median, because then the median is trying to eliminate the aspect of the outlier in your results. So it's a yes and a no. So you decide on how you utilize it based on your intervention. So if your intervention is really to first focus on those outliers, let's say your intervention is regarding population. So you have outliers will be those that are too rich, and then those that are very much poverty impoverished. So in terms of making an intervention, those that are too rich might influence certain decisions in terms of the buying and the selling of goods, but also they will affect the price range for the people who are poor. So then you'll also look at the ones that are very poor and say, okay, maybe this intervention, the way we had thought that since we are going to give people who are poor 10,000 shillings to improve their livelihoods, probably we need to increase it further because there are those that are very poor. Number two, you can decide to deal with extreme events or outliers separately. You can decide and say, you know what, for the poor, for those that are extremely poor, the intervention will be different from those that are moderately poor. And then for those who are very rich, there's also a different intervention, because it tends to appear that those who are very rich ends up being those who are very rich ends up to have other issues like social life problems. So the way you intervene to them will be a little bit more different. Yeah. So outliers can be good and bad in different ways on how you look at them. So what if we put also 4,000 on the histogram design? even though we do not have the value in our data. So this is an automated process of doing a classification, remember? So there is no any way you're going to have, you're going to put it there. It is using the data, the underlining data to split or to generate this histogram for you. The histogram is basically to help you to visualize the data, because you can't look at, let's say, population density of 1,000 or 5,133 records. You can't step by step keep looking at the attribute table and seeing and analyzing it. So this histogram really, really helps you to see how your data is being distributed within. Okay. All right. Somebody saying, shall we have a practical session? This is a theoretical concepts and principles of understanding GIS and remote sensing. So we may not be able to have a lot of practicals, but as you can see, I'm really trying to explain the practical scenarios as well as we are moving along. So for now, just pick the little that you can pick. For each of these concepts, if you feel like you want to understand more about it, please feel free. I'm going to show you at the end of the training where you can access some practical based way of applying them at a later stage. Aisha, your hands are up, so feel free to talk.
Yes, thank you, Thomas.
Yes.
Just a few minutes back, you've mentioned that it's an automated process. But when I look at the legend, the classification, the second group of 172 to 3422, I would like to think the third would start from 343. Sorry, 3423.
3423. So the reason is because there was a bit of a gap here, number one. That is one reason for explaining that. So that's one of the challenges. But also, I can't really explain why this came about in terms of, because I also expect it to be 3, 4, 2, 3, and then above. But for some reason, it has picked it to that. Maybe if you divide this by 3, like I said, it's an automated process. If you divide this by 3, you would get maybe a decimal point at some point, which is not allowed in this case. You can't have a population that is 10.3, for example. So that could also be the reason to explain this, that if you divide, someone had helped me and gave me a value. These are not even numbers. So if they were even numbers, then you would not have to have a decimal point. But I think at some point there was a decimal point, so that's why this thing decided to use 2 instead of 3. But also you'll see here that this value here is more like sitting alone. So probably if there was something in between here, it would be used for making sure that this classification is really okay. Then the other very most important thing is that the equal interval classification is done in such a way that for every class, there is the same number of groups. So there should be the same number of groups here, which is 171, 1,711. Also, this has to be the same number. So if this was maybe 304, then it would have made it 3, because then it would have the same number of groups inside here. So that is also one of the key reasons why it decided to use the 2, because it wants to satisfy that fact that for each of these, the groups in there should be the same number.
Thomas, I think.
But the middle one is 1710.
1710.
10. Yeah.
And then this one is what?
1711.
Okay, so I can't really tell why it decided to do that.
I think it can be confusing to anyone who would like to interpret, to see of those dark shaded ones, the third category. Is there any of them that actually would be falling in the second category, but instead is put into the third category because of that?
Yeah, so that is true. So when you run this classification, and I've done it a number of times, this is not a spatial statistic process. When you do a spatial statistics process, before you do a classification, the first advice that you should normalize your data. So normalizing your data tries to close those gaps before you actually run a classification. So for scientific purposes, if you're doing really in-depth trying to analyze your data, it's always advised that you don't use a classification as a method of doing statistical analysis or trying to analyze your data. The classification is basically for visualization purposes, so it is not accurate. For example, I'll tell you, if you decide to run kernel density analysis, because kernel density is using the mean as the proxy to identify areas that are highly concentrated. So you'll get a very, for visualization purposes, yes, people will just see it, but if you're actually doing an in-depth analysis, then you need to go further. First, normalize your data, use those statistical techniques to, first of all, clean out the outliers or try to minimize the effect of outliers within your data. And then you can now be able to do this. But also the classification process is, first of all, helping you by looking at the histogram to understand how your data is distributed, so that you decide how you want to analyze it. For example, you can use equal intervals that is based on a 3 split, or if you saw that, okay, this doesn't make sense. For example, on the ground, you know that the admin's boundaries of cities must be highly populated compared to those in rural areas. But if you do a split by 3 and you realize that some village districts are also having high population, then you realize, no. Let me try. So it is a test and trial process. So you can decide to split it by 3. And you need to explain that when I split by 3, it affects the output or the visualization output of the data. Then you can increase it by 4. You might realize that if you put it at 6, it again overstretches the data and makes it, because every time you split this data, you're stretching it in one way or the other. And this can be seen very well in remote sensing, which we'll do later. But also, like I mentioned, this is first of all to understand your data, and the in-depth look of your data is through the histogram, not necessarily through what you're seeing in the map, but the histogram, because it will give you a clear picture of how your data is varying from the smallest to the highest. Okay, I don't know if I've answered you. Okay, is there a GIS dictionary that can be shared? Sure, a GIS dictionary is available online. Just search for a GIS dictionary. You should be able to find a GIS dictionary. Maybe, yeah. Right. So unless there's any burning question, if I've not responded well, kindly let me know, and then I can give in more chips. I'm avoiding speaking too much because I don't want to overwhelm others who have not done a lot of GIS yet. So I'm trying to reserve more word, but if you've not understood very well, I can bring other examples that might give you a good light as we move along. So there's also one that is called equal area. So when you look at the two, look at the histogram, things really vary. Now, the equal area, you'll see that the black areas have increased further, and the gray areas have been Alan, I can't allow you to record, please. Sorry. Thank you. So you'll realize that the gray areas have been squeezed a little more and the black areas have stretched. So how does equal area? First of all, here is equal intervals. Now here is equal area. Now for equal area, the class boundaries are set such that the class has approximately the same total area. Now this is the area, not the counts. Initially we were looking at the counts. Now here it is looking at the area. So it's working based on, initially here it is looking at based on the counts of the number of admin boundaries. Okay. Now in this point, it's looking at the area measurement equal total area. Okay. Now you'll probably ask yourself, okay, which one is being influenced a lot by my data, how the data is distributed. So this often leads to a smaller range when groups of frequent classes are found. So the frequency that is being generated here is based on the area. So in this instance, the medium class spans a small range from 900 to that, while the high population class span a range that is almost 10 times broader from this value to that value. So this is about 1,100, 224 up to 5,133. So this is for the part 3, which is this range. Okay. So the equal areas are the ones that are being considered in this case. So you'll see that now it has moved from 333 to rather 1,223 to 1,224. So what we had anticipated to happen earlier has now happened in this point. But quickly, what you need to know the difference is because the other one is using counts, this one is using more like an area measurement. Okay, all right, so natural breaks they help a lot because for them normally it's actually the best. If you still don't understand your data, is to use a natural break. Let the computer decide how it wants the different counts of values to appear within the different classes. And then through it, you can now modify a little bit, either using a manual process or using the other mentioned automated process. So boundary between classes are placed where natural gaps or low points occur in the frequency distribution. So for example, if the population density is in such a way that, of course, these are frequencies. So this is not looking really at the population, but it's looking at the frequency of this total number of administrative boundaries. So let it not a little confuse you. The histogram is showing that for 100, how do I say it? So the frequency is telling you that for this population density, which is 1,000, maybe 500. How many parcels or how many districts have the same population here? Okay. So how many admin boundaries have this population? So that's what the frequency chart is showing you. So you'll see that these admin boundaries with population density of this value are 8 point something %. Okay, like that. And that's why you're seeing there's 8 point something % here, another 8 point something % here. There's another 8 point something % here. There's another 8 point something % here. So basically what it's saying is that how many times does the admin boundary or the parcel here has this population value here. So for natural breaks, it tends to split it in terms of the natural gaps that are available in the data. So how do I explain this? For example, between this value and this population value here, between that and that, there should be, it's just that I can't look at the attribute table. If I could look at the attribute table of this, I would explain to you that there's a big shift between this value and this value, and that's why it decided to get a break at this point. And there's also a big shift between this value and this value, and that's why there's a big shift between the two. Okay, so you'll ask yourself, why didn't it split from here? Why didn't it split from here, but still decided to choose that? Okay, but also all in all, in the natural breaks, you can also decide on the number of classes you want. These are the number of classes. Number of classes. Okay, so the data will be split based on the class number that you specify. If you decide 4, then you will have 4 classes. If you decide 6, then you will have 6 classes. But remember, like I mentioned, this has to be a logical process. You don't just throw numbers just because you want to make the map look nice, okay? Or some districts, if you're doing a study, you want some districts to look darker because you want to satisfy the interest of your audience when you show them the output product. No, it has to be logical in the number, because they'll ask you, why did you decide to use 3 classes instead of 4, or instead of 6, or instead of 2? So it has to be a logical reason behind it. All right. All right, Jean, cartographic analysis. Hopefully I'll show you some bit of some tutorials on hands-on, which you can follow up and be able to do more practice. It's a one step as you're moving towards getting into expertise or becoming an expert in GIS. Okay. The best way to determine the number of classes is by understanding your data and, for example, generating this histogram alone. Try to understand how this histogram is showing the distribution of your data. So, for example, you'll ask yourself, okay, I can create for me, I would even create about 5 classes. So what do I mean? I would look at my histogram, okay? And then I would split the one class maybe around here, so that I have this funnel shift to be outside. So this would be class number 1. Then I look at this up to this point, and then I would also split. So this would be the second class. And then I move up to this point, I split this, I put class number 3. And then I come here and I split this class also. This could be class number 4. And then I make this one also another class. And this would be class number 5. And then class number 6. So it's by looking at your data. And then if you put 6 classes, if you look at how the actual spatial features are being symbolized or rather classified, does it make sense? Okay. If it doesn't make sense, then you can say, okay, I think let me use 5 classes. But looking at your histogram distribution of your classes, and you can also do the histogram without going through the process of natural breaks. You just right click on the attribute that you want to classify. Then you look at the summary. You click on the summary or the statistical summary, and then it will show you how your data is distributed. There are different ways of testing for the normality, how data is normalized, visualize them as well, using the different statistical processes, which is beyond the scope of the course. Okay, so let's jump into geoprocessing part of analysis. We have looked at query or selection, but we also looked at the classification. Those are all processes that you do to do analysis. Now, another part is the geoprocessing point or stage of analysis. And for geoprocessing, you actually use the geoprocessing tools to perform analysis on different geographical data. Remember, this data can either be in a file geodatabase, or it can be in a relational database, or it can be in an object-based or object-oriented database. Now, there's times when you need to perform this process, and the first one we need to talk about is the dissolve. So the GIS dissolve tool is a geoprocessing tool, just like I've just mentioned, that is used to combine adjacent. You combine adjacent objects, which could be a polygon, a line, or a point, that share. They must share common attribute value into a single feature. Okay. So first you do a combination of adjacent, and these objects must share a common attribute value. So you can't dissolve things if they don't have the same attribute value. For example, you can't perform a dissolving when you for population density and maybe disease surveillance information. Okay, you only can dissolve for population density or for the area separately, not in combination of the two. So the dissolve tool can be useful in various applications, such as simplifying complex geometry, aggregating features by a shared attribute, and creating a new polygon layer from existing ones. So those could be the key things that you can do a dissolve on. In my class, I normally tell my students that in case you have admin boundaries of at a small level, let's say I have these admin boundaries, which are very tiny. Right now, there are 1, 2, 3, 4, there are 16 of them. And then I want to generate only 4, okay? I want to generate only 4 at the end, like this. I run a dissolve tool, so it is going to dissolve these ones, and this is going to be one polygon. Dissolve this would be a second polygon, and it will dissolve this to be the third and this could be the fourth. But remember, the underlying information, how this has to be dissolved is that this information should have the same attribute. Okay, it will be the same field that I'll be using to dissolve the polygons. So the resulting output from the dissolve tool will have a new set of attributes based on the shared values, such as the tool, the total area, length, or count. So these are the shared examples of the shared sorry, I had some internet hack a bit. I hope I'm sharing the right screen. Okay, all right. So for dissolve, if you look at this figure, initially it was having, let's say 1,100, 5,133 polygons. And now here it will be having less number of polygons. But remember, the dissolve that is being happening is based on the shared attribute. So in this case, anything that is white will be dissolved and it will form a single polygon. So I'll give you an example of this particular area. Okay. So you'll see that white is here, they are here, up to about here. So these are all polygons that are having a white color in them. So they have all been dissolved into a single polygon. Areas that are in gray, let's give an example of this part. Remember, they have to be adjacent. So you'll see that there is a bit of a merge in these areas, but they have left the middle polygon a little out. You'll see that the black one, this one cannot merge together simply because they are not adjacent. But if this was also black, then it would have merged this whole area into a single polygon. So those polygons must be adjacent to each other. Okay. All right. There's also something called the dissolve that is based on the attributes or looking at how the dissolve tool, when it is run, and what happens to the attribute table. So this is just explaining how the attribute table will change when you run a dissolve tool. So for example, you have a feature here. This feature initially here, attributes that looks like this. Okay. Now, what you're trying to say is, I want to run a dissolve tool to merge the different types of this. So that there are three types here. There's type 1, there's type 2, and there's type 3. So at the end of the day, I expect to get only 3 polygons. Those that are in type 1, type 2, and those that are in type 3. Okay. Now, of course, initially these polygons are not labeled 1, 1, or 2, 2, or something like that, but they are labeled A, B, C, D, and F, as you can see here. But because I have an attribute called type, I can decide to do a dissolve using the value type or the field called type. Now, when I run this dissolve, what's going to happen is that columns that are in value 2 are going to form a single column called value 2. Columns that are in value 3 are also going to be forming a column or a row called value 2. Then also records or rows that are in value 1 will also be merged and form value 1. Now, how did this happen? When you run a dissolve, what is going to happen that record 1 are all going to be combined here. They all be combined into one row. Then two are also going to be combined here. Okay. And 3 will also follow suit to 3. So instead of having 6 columns, yes, instead of having 6 records, rather the rows, you're now having only 3. And what it has done, it has used the column type to merge or dissolve those fields. Now, instead of having A, B, C, D, now you have X, Y, Z, meaning the naming has also changed. Now, the ID initially here was A, B, C, D, and then you would see A, B, C, D. Now, the final polygon here is having an ID X, Y, Z, and that's why the names are there. But what you need to note is that E and F has been merged into Z, C and B has been merged into Y, A and B has been merged into X. And then you'll see the cost value is not the same as the cost value here. Okay, so what has happened for row number 1 of value type 1 is a combination of 1,000 plus 2,000, which makes it 3,000. For 2, it will be 7,000 plus 9,000, which makes it 16,000, and so forth. Okay. All right. Now, that will also happen to all these other fields. Okay. All these other fields are also going to be summarized into this. Here we are only showing the one for the cost alone. So attribute aggregation is a key aspect of the dissolve operation in GIS. And I've explained this adjacent stuff. Now, the type of attribute aggregation that can be performed with dissolve tool include averaging, counting, maximum, minimum, and standard deviation. These options allow you to summarize in a meaningful way and obtain meaningful insight from your GIS data. So for this case, we have only done a sum. So we have summed this, but also you could say, you know what, for the standard edge, I want to obtain the mean of that, and then it will obtain the mean. So what it's going to do for value 1, it's going to pick this value 49 plus 83 divide by 2. That would be the mean. And then it will give you the standard edge, which would be the mean of that. So you can perform a number of these statistical parameters to generate the output values in the output admins attribute data. All right. Don't see any question. Let me see. No. Okay, perfect. In case you have any question and you want to understand how things are coming out, please just raise your hand. I'll allow you to talk and then you'll explain. Now, I've explained a lot of things, but these are basically the things that I was explaining earlier. So in this case, you're doing an average of standard edge, which I've explained. And then here, you're basically generating the sum of cost. So it will be this plus that. When you generate an average, it will be that plus that divided by that. And then also you can report the maximum based on the maximum. So in this case, we are reporting in the new dissolve tool output, or rather the new dissolve polygon, we are reporting the maximum virus report. So here, for the virus here, which is within this, you'll see that for value 1, there is 0 virus for this record A. And then for record B, D, for value 1, there is 9. So now it is reporting maximum. For value 3, for type 3 rather, there is 5. There's value 5, and there's also value 2. But instead, you're only seeing 5 here because 5 is maximum of 5 and 2. And then also you're seeing 1 for value 2 because there is 0 and there is 1. So meaning the maximum is 2. That's why you're seeing it 2. Okay. So how you want the output attribute table from the dissolve tool to look like, you make a choice based on those statistical parameters. Proximity and buffering. This is also one type of analysis that you can perform in within the GIS. So GIS proximity functions are tools that are used in GIS to analyze the spatial relationship between features based on their proximity, okay, based on their proximity to each other. These functions allow GIS analysts and researchers to identify, like I mentioned, spatial patterns. This is very key in GIS to determine the relationship, okay, and perform proximity-based analysis, okay? So let's say a nuclear bomb has hit a place. So when you want to now do proximity-based analysis, you can say anything that is proximate to this area has to be checked or tested or something like that. So these are the tools that GIS analysts can use to perform proximity-based analysis. The buffer, a buffer tool is a function that creates a zone of a specified distance around a feature, okay? So you could create a buffer around a school to determine which house fall within a certain distance of the school. Buffer tool is also used a lot in hazards. For example, if a flood has affected a particular area, you can create a buffer and find out how many houses have been affected along the river. Another one is a near. A near tool identifies the nearest feature to a specified location or set of location. So for example, you could use this function to identify the nearest hospital to a given point. So for example, if you work for hospitals or you work in the Ministry of Health and there's a pandemic there's an outbreak of a disease. So one of the things you can generate the GIS products or analysis or a service that shows for each of every area the nearest hospital that can be reached by the patients in case they have an issue. Distance, this function calculates the distance between features. For example, you could use this function to determine the distance between two cities. Also, we use this function a lot daily when you order an Uber. The Uber will tell you how much time it will take to reach you. And it's calculating it based on the distance. So it's saying the jam, there's moderate jam, traffic jam in this case. And then it will say, okay, the car is moving at 10 kilometers per hour. And the distance between you and where the Uber is maybe 10. So what it's going to do is it's going to calculate how much time it is going to take for it to reach you. So it will keep telling you 10 minutes, maybe 5 minutes to reach you. Intersect. Intersect is a tool that helps us in GIS analysis to identify a location where two or more features intersect. So you could use this function to identify a location where a road intersects with a river. All right, that's a clear example. Merge. This function or the tool combines features that are within a certain distance of each other into a single feature. So in this example, you could merge all the small towns that are within a certain radius of the major city into a single feature. So you realize that the merge does a buffering first. If you can perform a buffer first, or you can perform a selection, and then based on the select merge, so it will going to merge everything that is within a certain radius of the interest. So distance tool can generate something at the end. So when you run it, it generate polygons or circles that are a certain distance from the point of location. This is still also a buffer, and here we are trying to show how when you run a buffer, how the output look like when it's in a vector data model and in a raster data model. Yesterday we talked about vector data model to have a smooth boundary or a line for a particular feature, but when it's a raster, you have a bit of a stepwise sort of thing. But what is also very important to note here is that depending on the two data models that we talked about a lot yesterday, you can run a buffer on data, but also you can run it on a raster-based data. Overlays. Overlays are operations that are used Okay. All right. Eugene, thank you for stepping in to explain the dissolve tool. But let's continue. So overlays. So a number of geoprocessing tools are also used when you're going to perform an overlay operation. However, this operation is used to identify a spatial relationship. So remember, you're using two or more spatial layers. So in other words, you're trying to investigate the spatial relationship between those two objects. And you can use what we call the Boolean logic operation to do that. Boolean is basically a false or or true operations. You can do a yes or a no operations, okay, and so forth, okay. So those are the Boolean sort of operations that can be performed. So the resulting output can be a point or a raster data that has been generated based on a combination of two or more layers. So the tools that are mostly used during overlay operations are like the union. So it combines two or more layers and create a new layer that contains all features from the input layer. So what is very important is that the output product will contain all of the input products, and we'll see how that works. Intersection creates a new layer that contains features that are common to all. So in this case, it is not all, it must be common. So an intersect, okay? It's more like what we learned in high school, that during intersection, what is only common to both is the one that will be considered, okay? Now, difference, this operation creates a new layer that contains the feature from one layer. So something different. One layer and do not intersect. So it creates the final product which contains feature from one layer that do not intersect. So it is opposite of the other. So for example, if I have this, initially for intersect, it would be these features, yeah? Now for difference, it is going to now be these other features. Sorry, use the wrong color. So it will now be these other features that are not common to both, okay? Okay, not this part, only that is outside, that is common. Next is the clip. The clip tool creates a new layer that contains the feature from one layer that intersects with the feature from the other layer. So clip and it seem to things, but a little bit different, as we shall be able to see later. Of course, there's symmetrical difference. There's difference and the symmetrical difference. So operation of this kind creates a new layer that contains having a bit of power issues, on and off, but yes, we're here. So next is looking at the pictorial representation of the tools that we spoke about. So overlay. So you have layer 1, you have layer 2. So this could be the roads versus maybe, let's say, the cultivation fields or gardens. So when you join that, you create a final layer, which is called an overlay layer, which is a combination of the two layers. So here we are now trying to understand how the attribute table of the two overlays or overlaid layers would behave, but also a pictorial look of how things will look like. So layer 1 and layer 2 have this admin boundary, which is the geographic data, but also here they have the attribute data for each. So what happens when I overlay them? So when I overlay them geographically, I'll have 1, 2, okay, and 1 and 2. Now, if I overlay them Remember, if I overlay this one on top of this, the boundary, this boundary here is going to now be here. Like that. So now I'm going to have not only two polygons, but rather 4, which is a combination of this and this. So let's see, how does the attribute table work? So in this case, each polygon has not been combined like the way we saw earlier. It's still remaining separate. So initially it had 2 records, and now it has 4. So it has generated another extra 2 on this to cater for the records from the layer 1. Okay. Clip. So clip is basically, I've already explained what it does. So let me just explain from here. So you have, first of all, the catchments. Okay. You have the catchments, which is 1 layer. Then you have the counties, which are extra 2 layers. So later, when I overlay this with this and clip it, I'm going to have the output looking like this. So what is happening is that only areas that are common by this and that is what is found in the output. Anything that is outside, in this case, it's these areas. These areas are outside what is common in both layers. They are not shown in the final output. Intersection, it just, like I mentioned, almost works like a clip tool. What is only different between them is that for one, it's maintaining the other one, but also it's generating a completely different layer, as we probably see. So here, the color here is almost combination of the two, but here you'll see the colors are very different. So the extent of the clip layer boundary and the attribute of the both layer is the one that is displayed here. And then we have a union. So the union, remember, it considers in the output product information from both 2 layers. So you have this layer and this layer, which is 2, but then it creates another section which has a combination of 2, okay, which has the intersection of the 2 fields. Now, data from 2 layers are combined, including any areas that are contained by 1, but not both data layers. So no areas, no attribute data are discarded. So it keeps everything there. For these ones, it discards any area that is not common in between the 2. But for this one, it keeps all of them there. Blank or null values are typically assigned in the areas contained in 1, but not other layers. So when you run this in a GIS software, you'll be able to see how the null values come into play. But basically what they're saying is that what is areas that are not common by both, they are given a null value. However, they are kept in the final output. Okay. Erase tool is also one of the very important. It's like a rubber that you use for cleaning up a certain section of your data. So you have a future catchment and counties, and you can use the catchment as an erase feature. So it will remove any section which is intersecting the catchment in this case. Now, overlays, as we saw a lot in vector data, can also be performed in raster data. And I think they play a very, very big role when you're doing site suitability or spatial-based analysis. Now, like we saw, rasters are based on cells. and cells have values, and each of the value of each cell must have a dimension and so forth. Now here we have layer A with value AB, B, A, BB, AA, BB, or rather B. And then geographic feature layer B has 2, 3, 3, 2, 3, 1, 2, 1, 1. Now, when you perform an overlay, you're going to have a combination of that. So you'll have A, 2, B, 3, and so forth. As usual, it will also create extra attribute table for individual layers. So here, the attribute table for layer A has the soil name, okay, type and name. This one doesn't have the soil name. It has the land use. So that's an added attribute table. Now what it's going to do, it's going to create a column or a field for soil name, which is this one, and then also create another column for the land use as this one. So it's a little bit different from the way the attribute table will appear for vector-based kind of overlays and raster-based overlays, okay? So as you can see, it has not added rows necessarily down, but it has created columns for separate different layers. And in normal or in application based, you can have, for example, a population density layer together with the wind density or the wind direction or the wind layer. And then you can perform an overlay, select and perform a reclass. So those are three things you'll have done in geoprocessing. And through that, you get a suitability map for your product. So somebody will ask me that, how do I apply this? I mentioned to you that some of this analysis in the raster-based sort of analysis seeing a black screen, I see in the chat. I don't know. Is that the same response? Just type 1 in the chat. If you're seeing a black screen, type 1. If you're seeing a normal screen, type 2. Okay. So for people with 1, you should be having some issue. So kindly check your check your connection. Maybe something could have gone wrong. There's a question by Philemon. When performing a raster overlay, do your raster have to be same spatial resolution? Yes, but also no. You can decide to make sure that your raster data sets have the same spatial resolution. Of course, that will guide you in the final output, but changing the spatial resolution of a raster layer will not change the look of how the product is going to be. It will not change the, for example, if you do a resampling on your data, it doesn't change any information. All it does, it changes the dimension of the cell, maybe from low to high or from high to low. So depending on that, but the value or the information that is inside that cell, even though you change its dimension, will not change. So you can have them all in the same resolution, but not necessarily. What happens to attribute data B2? Okay, so B2 Where should B2 be? Do we have B2? I don't think so. So we have A, there's no 2 under B. So yeah, you're saying A3. Where should A3 be? So there is A1, A2, B1, A2, B3, B1. So some of the things you're asking, I don't see, unless you're asking them in terms of the previous pictures that I displayed. Okay, so let's wrap this training up by looking at the GIS applications. It's already 1, so I'll move quickly so that we summarize the training for the today. I don't want to overstretch it. So application of GIS, let's look at the one in business. So business, we can use it to cite or select where we want to put businesses or stores. So GIS can help a user to analyze spatial data to efficiently choose a suitable site for the store that they want to set up. Even in insurance programs, you can use GIS to understand who your customers are and their proximity to hazards so that you can offer a right product or service to them. In GIS, in insurance, products are based on the premium that the insurance company set for you. So for example, if you are in an area that will experience hazards more often, your premium might be a little higher than those that are probably in non-hazard prone areas. Citing a store is very, very important in GIS. So for example, you can use population density to first of all see where people are populated, but also you can use GDP data, gross domestic product data, to look at the buying muscle or the buying status of the people. You don't need to set up a particular kind of store and people buy cheap items or buy expensive items, and then you do the other way around. So you need to know how the population, how many people are in this area, and how many people have this level of income. Which kind of products can they buy for in case I bring these products? You might bring expensive products, yet your store has been set up in a low income area. So even though people are many, they can't afford the things you're selling. So you will not, your business will not flourish. People in the banking services have done a lot of analysis for this, and the financial services, they can use GIS, first of all, to understand the risk of their customers, but also do perform interaction with the customers. You can generate services, for example, site where you need to put an ATM based on the users, how many people are concentrated there. Of course, we normally use looking at the market areas to put our ATMs, but then also you need to look at the risk. Yes, people are many. There are people who have a high demand for these ATMs because the population is high, but is the place safe enough? So you can overlay a number of data sets. You use polygons, population data, then you use maybe information on markets, market locations. You overlay together with information on crime rates in that area. And then if aspects of power and all those things can affect you, you can look at the grid, you can obtain the grid data, overlay those three things together, run a bit of analysis, and then you'll be able to generate a right place where some of this can be implemented or placed. Another aspect, of course, is GIS application in education. So in education, we do a lot of field work and data collection. So GIS, together with the global positioning system, GPS, can enable people to collect data. And this could be in relation to look at species distribution, water quality, and other environmental variables that people can study, hydrology and all that. Visualization of the data, most of my students, they keep drawing maps. Others go further and perform analysis, very beautiful analysis, and they generate products which look at patterns and relationship between the different spatial objects that they have. Maybe others want to look at how the carbon generation is influenced by the vegetation cover distribution, how the land use is influencing the distribution of, let's say, the water quality, all this kind of analysis, some even including the use of satellite images. They can perform all this analysis using the GIS. And this is research-based, which is within the education field. Career preparation. I wanted to hint much on this because in all African countries, we are struggling with lack of jobs, but career preparation is very key when you use GIS. One, you can prepare yourself to be an analyst of different fields, looking at agriculture, focusing on hydrology, looking at the businesses that we have just seen, and all those things. Now, you need to learn how to use GIS, and the GIS tools and techniques can be able to be helpful to provide you a career. A career is not necessarily that you're going to earn money from it, but you can earn a reputation, you can earn professionalism, you can earn all these kinds of titles that you can have outside there. Of course, to come at a later stage with the financial benefit as well. GIS in governance. So planning and zoning, this is mostly done by district and city urban planners. Emergency response. So in every city, in every town, they have infrastructures for health, emergencies, and all that. Fire stations and all those things can be located suitably by the GIS, looking at the critical areas that need these emergency responses. Environmental managers use GIS a lot to understand and study the different environmental components, including the data on air and water quality, species distribution, land use, and for them, they can also use it to identify environmental hazards and develop strategies at the end to mitigate some of these hazards. Transportation planning are used by city planners, especially when they are trying to come up with new road networks, build new railway lines, looking at overlaying the population distribution, overlaying the infrastructure in terms of housing and all that together to plan for how the transportation of that can be done. Of course, in developed countries, we see so many planning done very well on transportation. In most of our cities and our countries, this is a total mess. And I hope that after this training and over time, we are going to improve this for our individual countries. Election mapping. Of course, politics is something that is very, very critical for the development of our countries, but also it has become, even though this is known or this is available, some of these techniques are not applied or nobody wants to use them, depending on their interest. But GIS can allow you, first of all, to set up where suitable areas where the polling or the voting can be performed, and how to fast track how the movement of the results are coming through, and how best to distribute the voting materials. You know, you can't have I'll give you, for example, in Uganda, we have districts that are in the far north and in the far east. Now, for some reason, people will set up cars that are going through a district, but they will not drop the polling materials there. They decide that each district will have a car that will take the polling materials. And yet you could plan it very well that as you're moving, you drop this off and you proceed to the other far end district. Okay. Healthcare, disease surveillance. We can use GIS to track the spread of disease. I did this for COVID for some institution in the country. You can look at how the disease is spreading, where are the high risk areas. You can use it to develop strategies to prevent the spread, as well as distribution and allocation of resources that are needed. Resource allocation, I've just mentioned that. GIS helps or facilitate the practitioners or professionals within this field to be able to know how best to plan for resource allocation. Emergency response, I've already explained on that. Environmental health, GIS can use to map and analyze environmental data, such as air quality and so forth that I've just explained. Community health is more like public health. GIS can be used to map demographic and health data at community level, such as rate of chronic diseases, access to healthy food options. This information can be useful for one to identify health disparities and to develop target interventions with the aim to improve the final outcomes. In natural resources, GIS can be useful in resource inventory. Okay, people go to the field, collect data on natural resources. You can be able to use GIS for this purpose. Impact assessment, I'm not explaining a lot of this and giving examples because these are obvious things. Impact assessment for every development that is going to happen, or a project, mining, logging, land use change, and so forth, needs to be assessed far before the actual implementation of the project. And through GIS, you can perform and predict the level of impacts the project is going to cause, depending on the different components in the environment. Land use planning, I've already talked a lot about this, that planners use GIS a lot to demarcate and partition the different, for example, in agroecological zones, all these plannings can be well done and mapped using the GIS. Habitat mapping can be used. We're going to have a full training course on habitats, natural habitats, mapping and surveillance and all that. This will be a hands-on course, but basically it's focusing on natural based ecosystems that we work with. So GIS will help you to identify areas that are important for biodiversity conservation and to develop strategies to protect these areas. Water resource management, GIS is very important and plays a very key role to understand the underground water aquifers, surface water, and so forth. And through this information can help to develop strategies to manage the water resources sustainably and to balance the competing water uses. So I've tried to run through some of this application in public safety, crime, emergency, disaster, and traffic management, as well as the asset management. These are things you can basically read and you'll be able to understand. They're straightforward. In utilities and communication, asset management, you can plan for the network and design the distribution network of the water and the power system. Service provision, you can, for those using cable TV, internet, phones, and so forth, all these are under communication technologies or services. emergency response and customer services. GIS can be used to map and analyze customer data, such as service requests and usage patterns. So for example, if an area you've seen a lot of requests or a lot of complaint happening, you can be able to identify, for example, how the utility is distributed in that area and be able to map it quite well. So this chart or this figure is not very clear, but shows a wide range of application and how you can decide to specialize in one of them. So thank you so much for today. I see a lot of chats. I hope there are not questions, and I will just summarize by taking you through the site that I wanted to show you, where you can access the hands-on materials. You keep practicing even before the actual training for this hands-on start. So there is a site called the QGIS tutorials. It's some of you could have seen it before. I'm going to just share it on the chat so that everybody can have the link to it. I'll also link it on the training site. So don't worry, you'll have that. And then QGIS is free of charge, so you can just download it and install it. Of course, ArcGIS is not free of charge, and under this program, we are being encouraged to tell people to use QGIS. But if you can afford to buy the ArcGIS platform, right now, ArcGIS Pro is the best application that you should enroll for. You have to pay a fee of 170 for you to be able to, and that fee runs for 1 year. So at $170 and for 1 year, I think that's a good deal. That should be really a good deal for you to do a lot of things with that. If you encourage your company or your farm to be able to purchase ArcGIS Pro, you can be able to get a lot of benefit from the software, because a number of tools, which I'm going to quickly show you, are available for you to run very, very important sort of analysis. So ArcGIS Pro is not free. It's a paid version. It's something that you have to pay for. But as I can probably show you, there are a lot of tools. There are so many tools that you can use for your analysis. So for example, here, I'm going to just show you a number of tools that have been introduced in ArcGIS Pro. So things like crime analysis, things like geoprocessing, geocoding, they're just patterns, analyzing a number of things that you want to do are all here. There's also a full-fledged raster functions, which I'm going to just show you quickly here. So there are full-fledged raster functions, things like NDVI, doing kernel density, computing change, running time series analysis. There are all these raster functions that you can have access to, and you'll be able to run all the kind of analysis that you would want to run. All this is available for hydrologists. All this is available. You can measure the height of the depth of the river, and all those things you can generate. There are so many function map algebras here that you can use to generate. The reclassification tool is also available. We talked about reclassification, remap. You can also work with, we're going to talk about remote sensing, but you can process Sentinel-1 data, run different type of processing on it. Under statistics, you can do all the statistical analysis. For example, cell statistic dimension, focal density, zonal statistics, and under surfaces, you can generate all these products, the digital terrain model, shaded relief, and all that from that tool or raster functions. So there are, I would call them over thousands of tools available in ArcGIS Pro. And they've also made it so easy to use for you. But also, of course, we have QGIS. As my QGIS opens, I'll give a chance to Jen to comment. Brian, please clarify, does ArcGIS Pro require you to fully register ArcGIS license? So ArcGIS Pro is still locked, so it's the cracked version is a bit hard to find. But basically, if you can be able to get the license, and Brian, for Makerere University, Esri is really pushing so hard to give us free licenses, and your school is spearheading this. So I pray that Doctor, you try and push for this so that we can have these licenses and forget about the cracked ones. I think Esri is ready to give Makerere University over 3,000 licenses, and all they're waiting for is for them to receive the documentation from us. Thomas, how many people are, you're missing the art in the beginning? Who is this? Somebody called Esa. Esa should be a laptop. I don't know who you are, but you need to put art. You look at the chart, the exact code, enrollment code of the course. Okay, let me give a chance to Jen. Jen, are you still there? I've given you a chance to unmute. Yeah.
Yeah, thank you, Thomas. I still have challenges with accessing the classroom. Kindly, if you're selecting a few people to, I had once accessed it, but now I cannot. So I don't know what's wrong with it.
Okay. So you're going to stay back, and we sort that after the session has been closed.
Thank you, Thomas.
Yeah, all right. So QGIS is also a very, very productive software. It has so many plugins. There are so many plugins that you can use within the QGIS software as well. So, I mean, this training was not really focusing on hands-on, but I'm just showing you that two major softwares can be used, and they can take you through step by step in the process of you learning. There are quite a lot of plugins that you can use. I have so many of them. I've used a lot of them, and they have worked for me perfectly fine. So if you can't afford the $170 per year, you can start with ArcGIS and you'll actually move fine. Of course, being a free version, you'll always experience the differences in the versions, and maybe some tools may not work and all that, but all in all, at the end of the day, you'll be able to do this, and you'll be able to finish, and everything will work fine. So thank you so much. Unless there's any burning question, I would like to request Doctor to close this meeting for today, and then we can be able to continue tomorrow. All right, Doctor, are you there? Maybe if you're not there, then I can just close the session for today. And then for those who are still having challenges, I don't know how best I can help. I could create a form and then. Okay, WhatsApp group might not work because these are unique problems. Okay, so just a quick reminder, I have already uploaded this material on day number 3. I've also split it day 1 and day 2. You must have gotten more like a message from me telling you that I've modified some things in the class. So you should be able to look up for the materials that have been uploaded. Also, the assignments that I'll be giving will be based on these books. So I'll be directing you to the different chapters for each of the assignments that you'll be receiving. So go through the materials immediately after finishing today. I'm going to also link the videos that you can be able to watch and go through them again. Thank you so much for those who have endured up to this point, and I wish you a good afternoon. Thank you. Bye.